All right. The next speaker is going to be Minji Shen. He is a PhD student from Purdue University.
Yeah, hi, I'm Minji Shen from Purdue University. I'm glad here to present our work on automated identification of layering violations in embedded applications. We thank Rolls-Royce for their support. Our contributions are, first, we develop a static analysis tool to detect a class of layering violations called Non Conventional MMIO Accesses, or NCMAs. Second, we create a large data set of compilable embedded applications containing 988 applications spanning on 5 RTOSes. Third, we identify 369 NCMAs and found developers' reasons of committing layering violations. So let's first talk about the background and motivations. So to reduce the difficulty of porting, the embedded software applications is organized into layers that communicate only with adjacent layers. If application follows this design, it simplifies supporting a new microcontroller unit as only one layer is impacted. So let's see a simple example application that follows the layered design. It interacts with only the adjacent layers through the GPIO API function, which is highlighted in the code, to periodically toggle an LED pin. This application compiles and runs on all the boards supported by Zephyr. The core graph on the right shows Zephyr's layered design and its abstractions for the vendor-specific hardware abstraction layers. So when applications commit layering violations, its portability becomes worse. Specifically, we want to focus on a kind of layering violation related to hardware or peripheral access. Most peripherals are accessed by MMIO. An application should access these memory regions through a hardware abstraction layer. When applications violate this principle by directly accessing MMIO without going through the HAL, we call such access as non-conventional MMIO access, or NCMA. Here we show a simple example code that directly accesses the timer peripheral through a hard-coded MMIO address by first casting it to a struct and then accessing its member. So now I will present the details of HAL-VD, our automated technique to detect NCMAs. So our goal is to report there is a NCMA in function X at line Y in file Z. So given the application's source code, we first automatically convert it to the LLVM bitcode using the custom build monitoring. Next, we identify all MMIO access by performing a lightweight analysis of the LLVM IR. And finally, we use heuristic on the core graph to determine whether a given MMIO access is actually a NCMA. So we want to use the LLVM compiler infrastructure to implement our analysis. However, it requires whole program bitcode, that is, one bitcode file for the entire embedded application. Generating whole program bitcode is challenging, and prior work manually modified the build scripts like makefile or CMake lists. And we partially automate this process through the runtime build monitoring. We monitor the build process of an application to capture all the compiler invocations and translate them to the corresponding bitcode generation command in clone. And finally, all the generated bitcode files are linked together into a whole program bitcode. So almost all the embedded systems use a GCC-based toolchain, and the translation to clone involves 4 challenges, and we solved all of them. And all of our treatments are semantics preserving. So after generating the LLVM IR, we want to find all MMIO access functions. So the intuition is that the MMIO is usually accessed through hard-coded address, as is shown in this example. Thus, the heuristic is that we can identify MMIO access by identifying any memory access instructions whose pointer operand is a constant. So after finding all the MMIO functions, we need to identify NCMAs among them. So NCMAs occur in non-HAL functions that directly access MMIO. We distinguish between HAL and non-HAL functions by the transitive in degree or IDT of nodes in the code graph. The idea is that HAL functions expose necessary functionality and consequently are called by many functions. As a result, in the code graph, HAL functions are reachable from many functions above the HAL layer, and thus having higher transitive in degree than the other non-HAL functions. Thus, we designate nodes with IDT higher than a predetermined threshold lambda as HAL functions. So for evaluation, we compiled 988 embedded applications and runs our tool on them. These applications run on 5 RTOSes. So first, let's evaluate MMIO Access Finder. So for false positives, specifically in the 500 plus free RTOS applications, free RTOS defines some HAL functions as C macros. If application functions call these macros code of direct MMIO access is expanded at the body of these application functions, and thus this application functions is incorrectly identified as making direct MMIO access. We also find cases where hard-coded address is actually normal memory regions instead of MMIO address. So for the false negatives, these are actually expected because we don't use any alias information, but none of them are NCMAs, so they do not harm our final goals. So now let's evaluate the effectiveness of NCMA identification through the code graph heuristic. We did find quite a few false positives and false negatives. Certain HAL functions expose an uncommon peripheral and that they may not be needed by many functions and consequently have lower IDT. False negatives result from popular application functions with IDT higher than lambda. Some application functions may be needed by many other application functions. So in the future work, we will identify HAL functions based on the directory structure of the source tree of the embedded application. For example, we can consider all the functions under a certain directory as HAL functions. So a few developers agreed that NCMAs need to be fixed. But there are 2 cases where developers believe NCMAs are fine. First, certain applications support only one platform and non-portability is therefore acceptable for them. Second, some HAL APIs have unexpected behavior. For example, a timer driver might clear a register before developers can read its value. So how developers might use this information to improve their APIs. So these are codes from the developer response. So in summary, we developed a static analysis tool to detect non-conventional MMIO access and found 369 NCMAs in our dataset. So we thank Rolls-Royce again for their support, and here are my contact information and our artifact. Thanks for your attention.
Thank you. I think we can have a quick one question. All right, then let me follow up. Could you talk a little bit more about the user study? Do you reach out to them individually and then got the responses?
Yeah.
How could you share your experiences a little bit more?
After we detect NCMAs in their code base, and I write GitHub issues and ask them, they are doing the direct MMIO access outside the how functions. So I think that this might be a problem, and they explain that their reasons for doing that.
And then are they responsive?
Some of them respond and others just ignore.
All right. All right. Thank you. All right. We have